Thank you very much, Sonia, for this nice presentation. I will now give the floor to Vincent Pocheux. So
Thank you very much.
thank you very much. The three first presentations were about production. So now let's move to the storage world. So Vincent Faucheux is senior researcher at CEA. He's actually a colleague of mine. So he's going to present something about liquid organic hydrogen carrier. So Vincent, the floor is yours.
Yes, can you hear me? I try to share my screen.
Yes, we can hear you. But we still don't have your screen shared.
Okay. I have trouble to have my presentation.
If you want, Vincent, we have your presentation.
Yes, if you can share it.
So Gemma, can you share the presentation? If you hear me, I can do it. Okay, I'm going to share it. Please tell me when you see my screen. Can you see my screen?
Okay, fine.
Okay.
So, hello everybody. So I'm going to present you some development regarding the LOHC technology. So LOHC means liquid organic hydrogen carriers. And today we mainly focus on the SHERLOHCK project, but I have also some introduction, 2 or 3 slides just to explain you the reason of the existence of this project. So next slide, please. So I imagine everybody knows this, but just to explain you the context of such project. So we all know that we will have a production of electricity from renewable energy, which is highly intermittent. It means that we will have to develop some storage technology compatible with large scale of time and capacity, and if possible, also compatible with existing transport infrastructure. So hydrogen can be used for such storage technology, but we have today 2 different technology with quite high maturity. I mean, liquid hydrogen or liquefied hydrogen and compressed hydrogen. But none of these 2 technology completely fulfill all the requirements. It could be issue with safety, with boil off, with cost, for example, for liquefaction. It means that we have to develop some new hydrogen carriers. So next slide, please. Now, if you consider the new carriers, you have different possibility, but the tail level of these different possibility are quite low, between 2 and 4, for example. Today, we are focusing on the chemical storage. So chemical storage could be an alternative for the transport and the storage of hydrogen for safety reason, because you have strong bonding between hydrogen and other chemicals. So you don't lose hydrogen during transport, for example. So in terms of safety, it's a good point. And the other aspect is the fact that you can have a high content in terms of hydrogen. You have 2 different possibilities. You have the liquid possibility or the solid possibility. For the liquid possibility, you have mainly the LOHC, so the goal of today, of this presentation. So I will explain in detail the different advantages in the next slide for the LOHC. And the other aspect is the solid storage, which are also interesting, mainly due to the high hydrogen storage capacity, more than 10% in terms of hydrogen capacity in weight. The main drawback of the solid storage is the regeneration. Today, it's only a 1 cycle system. It means that in terms of application, we are just addressing the niche market application, for example, submarine. So now if I come back on the liquid storage with the LOHC, so please next slide. I just explain you in 2 sentences how it works. I don't know if everybody knows. So you have a pair of molecule, for example, toluene methylcyclohexane or dibenzyltoluene, pyridodibenzyltoluene, so the 2 main molecules studied in the literature. And you pass from one molecule to the other one through a catalytic hydrogenation or dehydrogenation. And for this, you need temperature, pressure, and catalyst material. This system is reversible. It means that you can obtain hydrogen and the lean LOHC, but the lean LOHC, you can use it again and again. So it's a multi-step process. And the goal in that kind of technology is to use the LOHC 100 or 1000 times. All these molecules are transported in a liquid phase. So it means that you can use truck, shipping, pipeline to transport the molecule. So it's compatible with the existing liquid fuel infrastructure. You don't have hydrogen loss due to the chemical bonding, which is a good point, as I told you, in terms of safety. And you can store hydrogen with a maximum of about 7% in weight, if you compare with the 5% for the compressed hydrogen at 700 bars, for example. Another positive point is that the proof of concept has been demonstrated by different companies in the world, mainly in Japan and in Germany. But you have some drawbacks for such technology, for sure. So next slide, please. And the different drawbacks are on different aspects of this technology. The first one is related to the molecule, the choice of the molecule. Today, most of the molecules have need a lot of energy during dehydrogenation, between 60 to 70 kilojoules per mole of hydrogen, which is about 20 to 25% of the heat capacity of hydrogen. It means that if you have 4 or 5 molecules generated during dehydrogenation, you have to take one, to combine it with oxygen to burn, and to use the heat to realize the reaction. So you decrease the yield of 20 to 25%. So it's a first drawback. The second one is regarding the catalyst material. Today, for all of this reaction, you need PGM, and you need a lot of PGM. I just give you a number. If you have a connection to a fuel cell with a yield of 50%, so just an hypothesis, if you want 1 kilowatt, so electrical kilowatt, so useful kilowatt, you need about 1 gram of platinum. Okay, so for example, if you want to use it in a car, you need about 20 to 25 grams of platinum. So it's a lot. And the other aspect is regarding the reactor or the system. Today, you have a low thermal exchange between the catalyst material and the support. And also you have a bad exchange between the molecule and the catalyst. Why? Because during the dehydrogenation, for example, you have, for example, 1 cubic centimeter of LOHC, which give 1 cubic centimeter of lean LOHC, but also 1 liter of hydrogen. You multiply by 1000 the volume of your system. It means that the reactors are full of gas and not liquid, but the gas, the hydrogen. It explains why we have a bad thermal exchange during dehydrogenation. So, and if you have a bad thermal exchange during dehydrogenation, the reaction is on the thermal. It means that you have some cold spot. So you have a lot of PGM, and if you have cold spot, it means that you don't use the PGM you have integrated in the reactor. During hydrogenation, you have some hot spot because the reaction is exothermal, and it means that in these cases, the temperature of the molecule and in some part of the reactor are upper the targeted molecules, the targeted temperature, sorry. It means that you can have a degradation of the molecules. So to maintain the temperature constant in the reactor, is another goal we have to reach with this technology. And the SHERLOCK project has to address these different drawbacks. So the goal of SHERLOCK is to develop materials and reactors to improve the performance of the technology, mainly during the dehydrogenation step. So the project has started at the beginning of this year. So it's a 3-year project. And at the end, we have to target a TRL level of 4. In the consortium, we have, so we are the coordinator, and we have different partners from Germany, which is today leading this technology in Europe, mainly with hydrogenous technology and with the University of Erlangen. But we have also some partners in Netherlands and Spain, and one in South Africa for the predictive analysis regarding the catalysts. So next slide, please. So the objective of this project are mainly focusing on the catalyst improvement. So here you have some numbers indicated here regarding the energy of our system, regarding the kinetics we have to reach, and regarding the stability and the durability of the material we are developing. So the final objective of SHERLOCK is to unlock the full potential of the LOHA technology. Some demonstrators are existing in the world that the proof of concept has been demonstrated, but we have to clearly show the economic relevance of this technology. Next slide, please. So the approach, so it's, I would say, quite simple. It's to optimize the different components which are existing in this technology. So from the molecule, so from the catalyst to the reactor. So for example, for the catalyst material, we start from a DFT analysis with bimetallic material, so platinum, tin, platinum, cobalt, platinum, copper, for example. So we have some DFT analysis leading by the team in South Africa. And in parallel, we have some development with the same kind of material, but experimentally by different partners in the project. And the goal is to have a convergence of the experimental results and the result obtained by DFT. For the architecture of the reactors, we will use the 3D printing. We know that 3D printing is not able to be used for high throughput, but the goal of the 3D printing is to develop some new and specific reactors just to study in specific condition the performance of the catalyst we have developed previously. And at the end, we have some different work package regarding the testing and the scale up of what we could develop in the project. So next slide, please. So just here, first result, just focusing on the development of catalyst material. So the goal is to decrease the quantity of PGM material in such technology. So for sure, it will be better to have a PGM-free system, but we are going step by step. Today, we are developing bimetallic materials. And here we have a result with an association of platinum and tin. On the right, you have some picture about the size of the particle, which are around 1.5 nanometers. And the testing in dehydrogenation, we can reach about 2 grams of hydrogen per minute and per gram of platinum. So today, these results are better than the one obtained with pure platinum. So we have to confirm this result because we have to be sure that we use the same quantity of materials and we have the same microstructure of materials. But this is the first result, which is interesting here. So the next step are to verify that between DFT and experiment, we focus on the same results. We also have to integrate such materials. So today it's on alumina, but to integrate them on carbon support because the thermal conductivity and electrical conductivity of these materials are better. And at the end, to integrate these materials in new architecture, which are developing in parallel. So next slide, please. This is the last slide. In SHERLOCK project, we are focusing on different aspects, but SHERLOCK project is not addressing all the challenge we can have on this technology. The first one is that today we only focus with existing molecules, so dibenzyl toluene or benzyl toluene, but for sure we have to develop some new molecule with lower enthalpy of reaction to decrease the energy need during the hydrogenation. So today we have some DFT analysis regarding this aspect. Another thing is that even if in the project, SHERLOCK project, we have some development on the interfaces, we have to go deeper by integrating in operando characterization. And it's not maybe focusing only on material, but we have also to integrate some alternative processes to decrease the temperature of degeneration. For example, if you consider the fact that the heat generated by the PMFC is more important than the need in energy during dehydrogenation, you could use this heat. But the fact is that the temperature of the PMFC is at about 80 degrees, and the temperature of the direction is at between 200 and 300 degrees. It means that today it's very difficult to have a thermal coupling between the fuel cell and the reactor of dehydrogenation. So the goal is how we can decrease this temperature in the reactor to be compatible with the temperature of the fuel cell. And at the end, another thing is that we can adapt what we learned today on the LOHA to ammonia. Ammonia is not a LOHA, it's not organic, it's not liquid after decomposition of ammonia, but the behavior of this molecule is quite similar to the one we have in LOHA, so we can adapt the system to ammonia. Thank you very much for your attention. If you have any question.
Thank you, Vincent, for your presentation. So I see if there is any question. So actually there is not at the moment, and I think we are going to move. Yeah, there is one question. How can the LOHC technology built on industrial hydrogenation, dehydrogenation process?
In fact, you have two kinds of technology. Today you have, for example, the concept developed in Germany, which is mainly focusing on stationary application, I would say small scale. And the one developed in Japan with Chiyoda, it's a large scale. You have to transport hydrogen between one country to another one. The hydrogenation part, it's quite easier to investigate how it can work because you just have to produce hydrogen. You can use solar energy or wind energy. It's not so difficult. The difficulty is during dehydrogenation, because here you have some small plants, because you need your hydrogen for different applications with different spots in the country. So the difficulty here is how we can build a business model on the dehydrogenation, because each time is supposed to develop a reactor, with platinum and with a safety reason, with different aspects, and the integration of this dehydrogenation plant in many spots in the country is quite difficult to integrate, mainly for this reason, and the cost, on the impact on the cost of this technology.
Okay, and maybe last question, because we are a bit late, from Bertrand Solvay. Why not coupling LOHC to high temperature PEM to have a better thermal matching?
Yes, but I had in mind that the high temperature PMFC were not at a quite high level of maturity, and maybe I'm wrong, But if we can find some high temperature PEM, it could be a good opportunity because you can directly use the heat from this PEM. It could be used also with the SOFC. It's another possibility. But if we can have a high temperature PEM, yes, it's a good idea.
Okay, thank you very much.
Comment on that. I think that the high temperature PEM is pretty mature. That's not the issue, but it is most suited for working with reformers like for methanol and reforming. The cell voltage of the high temperature PEM is somewhat lower than the low temperature PEM, so you get a little less out of it. So the big benefit is when you can tolerate the impurities of a simple reformer without purification for carbon monoxide. So if you have pure hydrogen available, it's better to run with a low temperature PEM fuel cell. Just a comment.
Okay, thank you. Thank you, Jens. We have to move forward. Thank you very much, Vincent, for your nice presentation.